Hi, this is Professor Fernandez, and in this video we're going to work out an example of the trapezoidal rule error. This example comes from the lesson notes from lesson 18. You'll find those notes on this website, along with those other resources. So trapezoidal rule is a numerical integration rule that takes a problem of finding the area under the curve, let's say between a and b, right? For this function y equals f of x, that would be this area. And we know that that's equal to the the definite integral from a to b of the function f of x. So this area, we call it a, and a equals that. The trapezoidal rule says we're going to approximate this by using trapezoids. There's various ways to introduce the trapezoidal rule, and we have formulas for that, and all that information is contained in the lesson notes for lesson 18. But just to simplify matters, let's say I subdivided AB into 3 equal subdivisions, right? Then we would have these y values of the function at those corresponding x values. And the trapezoidal rule basically takes these information and draws trapezoids, right? To try to approximate the functions, the area under the function's graph with the area of these trapezoids. So if I were to add the areas of all these trapezoids, in this case there are 3, 1 to 3, then I get an approximation to the actual area under the curve. So that's the trapezoidal rule. And as I mentioned, there's systematic formulas. There's systematic ways to do this, and they lead to formulas for actually calculating the area of those summed trapezoidal areas. One thing in this video, though, is we don't necessarily ahead of time know how many trapezoids, right, to add up, how many trapezoids to use if we're going to add up their areas to actually approximate any given definite integral within whatever error. So the question arises, how do I figure that out, right? Is there a way that I can choose an n value that will get me to within a specified error of the actual area that I'm trying to approximate? And there is a way to do this, and it has to do with some of the theorems that relate to the error in that trapezoidal approximation. So one of those theorems is down here. This comes from, again, the notes for lesson 18. And I'll encourage you to pause the video and read over the theorem, but I'll just jump to the salient portions here. So long story short, there are some requirements that we need to verify in order to use this theorem. The function has to be integrable. It can't have an infinite area under the curve. It has to either always be concave up or concave down on the interval we're going to integrate it over. If that's true, then we can get both information about the error, and if also the function's second derivative is bounded, at most some number u in absolute value on the interval, then t sub n here, error e sub t sub n is the error in the trapezoidal approximation. We have a bound for that. So recap, right? If the function's integral is finite, it's not an infinite area, it's either always concave up or concave down. And we know that the second derivative, which measures concavity, is at most this u, whatever the u is that we'll calculate in a minute. Then the maximum error in approximating the definite integral by the trapezoidal rule approximation is this thing over here. Okay, so now let me show you how to use this information to help us calculate how many trapezoids we would need to use in a trapezoidal rule approximation to get to within a certain error of the actual value for that area. All right, so that's exactly what this example says. I'll zoom in a little bit. What n value guarantees that a trapezoidal rule approximation to this will be accurate to within that? Okay, so first of all, let's check all the hypotheses of this theorem. The function that we're integrating here is 1 over x. Okay, if we draw this function from 1 to 2, we see that the area that we're calculating is finite. So that was the first assumption, check, finite area. The second assumption was that the function is either always concave up or always concave down on this interval. We can see that in this case it's always concave up. We can verify that, and we'll kind of need to do this anyway by calculating the second derivative. So this is x to the minus 1. its first derivative is minus x to the minus 2. Its second derivative is 2x to the minus 3. Because on this interval, the x's are positive, 2x to the minus 3, this is 2 over x cubed, right? This quantity is also always positive. So we verified mathematically and graphically that indeed this function is always concave up on this interval. Great. So now the second thing we want to do is, now that we verified all that, we would like to find the maximum of this second derivative. Okay, so there are two ways to do this. You can do this graphically. So if you were to graph the function 2 over x cubed, we're only interested on this interval. You can plot a few points, right? At x equals 1, if I plug that in here, 2 over 1 is 2. So that's here. At x equals 2, this is 2 over 2 cubed. 2 cubed is 8. 2 over 8 is 1/4. So that's really tiny down here, 0.25. And the denominator is cubing x. So the larger x gets, the larger x cubed gets, and the smaller the fraction gets. So you can reason this out, that the graph is going to look like this, or you can actually just graph it. Long story short, this tells us that the second derivative on this interval, which is all we need, is decreasing. So its largest value, its largest y value is here. Largest y value is 2. So back to the absolute value of f double prime, it's less than or equal to 2 on the interval 1, 2. Okay, so now we have all the information we need to actually apply the theorem we talked about over here. So now let's go back and see what it tells us. So if I focused on this part, here we are, it tells us that the absolute value of the error in the trapezoidal rule using n trapezoids is at most u was the bound on f double prime. Scroll back over here. That bound was 2. So is at most 2 times b minus a cubed over 12n squared. So let's get all that information. First of all, we don't know n. That's what we're trying to find. How many trapezoids do we need to use to get the trapezoidal rule to within a certain error? Okay, how about b minus a? We do know a and b. We've been talking about the interval here. It's the interval 1, 2. So b is 2, a is 1. So now if we calculate this here, we got 2 times 2 cubed, that's 8, divided by 12n squared. Or actually, oops, small mistake there. 2 minus 1 is 1, so this is 2 times 1 cubed. So that's 2 over 12n squared. So that's 1 over 6n squared. Okay, great. So now at this point, we know what the maximum error is going to be. Less than or equal to this, no matter what n is. So now we can use this information and go back and look at the error that the question is asking us for. So we want to find the n value that guarantees the approximation will be accurate to within this much. We've just found that the maximum error in the approximation is 1 over 6n squared. If we want that error to be at most that, then we say this less than or equal to, right, 0.001. And that's tenths, hundredths, thousandths, that's 1 over 1,000. Okay, and then now we're left solving, oops, I don't know what happened there. We will try that again. There we go, sort of. And then now we're left solving this less than or equal to that. So let's do that. 1 over 6n squared less than or equal to 1 over 1,000. Take reciprocals, both sides, changes the inequality sign. Divide by 6. And then take the square root of 1,000 over 6. If you calculate this, this ends up being about 12.9-ish. So the conclusion is that n bigger than or equal to 13, we want the next, quote, whole number, right? Because remember, n is how many trapezoids? You can't have like 12.9 trapezoids. You can have 13 or 12. So if n is larger than or equal to 13, in other words, you use at least 13 trapezoids in the trapezoidal rule approximation to this area, this represents an area, right? Then you are guaranteed by this theorem down here that the error in that approximation will be at most 0.001. Great, so that's how you use this theorem to actually help you figure out how many trapezoids you need to use in your trapezoidal rule approximation to get within a specified error. Thanks for watching.